Hello and welcome back. Today we are discussing section 2.3, product and quotient rules, along with higher order derivatives. This first video we're going to tackle just the product rule piece. So just something to get us kind of thinking about the issue. So our quick example asks us to address two very similar looking derivatives. So one of which is an obviously easy to simplify thing first before we take the derivative. And the other is those two component pieces, so x squared and x cubed, broken up into two separate derivatives. So basically our curiosity is the following. Are these two numbers equal? That is, does this product right here get ignored by the derivative and let us take the derivative of one thing and the derivative of the other separately? We know it does this if one of them is a constant. If this was 5 times x cubed instead, we'd be in business. We could pull that constant out, no problem. But the curiosity is, can we do the same thing if each of these has variable components? Okay, so first computation, we do the simplification first. So we're not going to mess around with trying to do these pieces separately. We'll just rewrite x squared times x cubed as x to the fifth. That's just using our power rule. Or rather, rule for exponents. And now our actual power rule for derivatives, bring the exponent down to get 5 times x to the fourth. Second computation, so this is two separate small derivatives. So the derivative of just x squared by itself, using power rule, gives us 2x. And then if we do the same thing for x cubed, here's our second derivative, still power rule, we get 3x squared. And then with the last little bit of simplification, we can turn that into 6 times and then x to the third power. So this is kind of bad news. We did not get the same answer in either case. So because these two expressions are not equal to one another, the basic conclusion is I cannot break derivatives up over multiplication if there are x's in each of those pieces. The only time we can sort of pull one of the pieces out is if there's a constant. So all is not lost, however, if we've got two functions and each of them have derivatives that exist, then we have a rule. So product rule, remember the word product just means multiply things together. So this is a rule for when we've got two things having variables in them multiplied together. So basically what it says is that we need to let each function vary. So f prime is the rate of change in f, g prime is the rate of change in g. So we still have to use those derivatives, the f prime and g prime, but we use them and multiply by the other function, the other piece that's fixed. So f prime gets multiplied to g, and then we add to that the other combination. So imagine sort of moving the prime from one function to the other. Now we leave f alone and take the derivative of g. So the sum of those two component pieces gives us the derivative of this product. But the main thing to avoid is not to just multiply f prime and g prime together. That's not the rate of change in this product, unfortunately. Okay, so let's put this into practice with our initial example, and we'll try that x squared times x cubed thing, but with the product rule. We don't have to define things this way, but we can use the actual definition of the product rule and identify which of these pieces we're going to work with. So let's just call f of x stuff red and g of x stuff. F of x stuff is going to be cyan, the x squared things, and then the g of x stuff will be red. So our product, x squared and x cubed. Again, I'm not claiming that this is a smarter idea. Doing all this is smarter than combining x squared and x cubed. All I'm trying to do at this point is identify that this product rule does let us correctly compute stuff. And since we already have an answer for this derivative, we can compare this new thing with our old process. Okay, so f prime, here we go. We've got anything in cyan, it has to do with f's. So here's f prime piece. And there's f just left alone, no derivative stuff tacked onto it. And then similarly for our g of x stuff, x cubed is our g of x. And then g prime over here, we're asking for the derivative of g. So this is just our product rule theorem, basically. So we've taken, and we're getting a little bit more familiar with this, but we're taking what is a more complicated derivative that we have trouble with and breaking it into, in this case, two smaller component derivatives that are easier for us to figure out. So this ddx, again, is just a set of instructions. It says take the derivative of whatever's to the right of me. So derivative of x squared, using power rule, gets us to 2x. And the derivative of x cubed, the only other derivative that's part of this expression, derivative of x cubed, again using power rule, is 3x squared. So since we've computed both of the derivatives that we were asked to in this previous line, all the calculus stuff is done here. The only thing that's left is to combine like terms and add exponents if possible. But if you notice, this is 2x to the fourth, and this ends up being 3x to the fourth, so they actually are like terms. They combine to give 5x to the fourth. And very comfortingly, at least for me, I don't know about you, but this agrees with our initial computation when all we did was first combine x squared and x cubed. So if you glance back at our quick example, just rewind a little bit, you should see that this is the same answer. So let's try, that previous example was basically just to prove that product rule doesn't give us something that's wildly inconsistent with what we've seen so far. Now let's actually try it in a situation where we're just identifying product rule as the thing to do from the beginning. Okay, so we're going to say that demand for some basic model smartphone looks like this. This is how many D1,000 phones get sold when we charge P $100 per phone. And the actual task for us is to figure out at what rate is revenue changing with respect to price. Now, I don't have a revenue function just yet, but we can get one. So revenue, if you recall, is going to be built out of component pieces here. And in general, it looks like how much we sell times the unit price. So in this case, we have a unit price of P, and we have a quantity sold of this demand function. This phrase, with respect to, it comes up with derivatives more and more frequently as we start to look at more complicated inputs. With respect to price just means that we're taking the derivative. So if we had to write this as some kind of our derivative operator, instead of ddx or ddt or something, p is the input variable. That's all it's really telling us to do. And what we're supposed to do is eventually figure this out when charging $200 per phone. So that sounds like a unit price, and it is. The only thing we have to be careful about is that P is already in hundreds of dollars. So $200 per phone is actually P equals 2. Okay, so the first task in front of us, though, if I want a rate of change in revenue, I probably ought to have a revenue function. So that's our initial task. So we've got P times demand, unit price times quantity demanded. And then we replace our demand function with, our demand expression with the actual formula for it, 12 minus P squared. And this is a reality check moment. I'm perfectly cognizant of the fact that we could take P and multiply this through, and then we'd have a nice polynomial. We wouldn't need to use power rule, or product rule. We could just use power rule. But for the sake of using this and getting familiar with it, because there are instances in which it is mandatory to use product rule, let's just apply it in this case, and then note that for this particular example, moving forward, we could have just used a simpler strategy. So the thing we're supposed to pay attention to is that we have two distinct pieces here, things with variables in them getting multiplied together. We have P, and we have 12 minus P squared. So the product rule, unless we expanded, and again, I'm not claiming that's off the table, just we're not doing it here so we can explore product rule. That means we've got two things with variables getting multiplied together, and we want its derivative, thus product rule is on the table. So we follow through with this definition again. We've got all the stuff to do with our first function, and we can continue to refer to that as f if you'd like. So the f function is just p in this case. And so those are all the pieces that have to do with f, either f prime or just the function itself. And then we've got our other pieces. So this is our g of x back again, if you will. And then g prime is this derivative we have yet to compute over here. Okay, so we've at least set up what product rule is supposed to look like. Now we take the derivative of those pieces, the derivative of p with respect to p. This is like the derivative of x. Maybe that's the best way to think about this moving forward. Derivative of x is just 1. Derivative of p, where p is the input variable, is just 1. And then the derivative of 12 minus p squared is power rule in each of those pieces. The derivative of 12 is 0, so that's out of there. Derivative of negative p is right here, negative 1. And the derivative of negative p squared by power rule is this chunk, negative 2p. So there's no more DDP instructions here because we took all the derivatives we were supposed to. Now all that's left is some algebra. So 1 times this doesn't get any better. P times negative 1 is negative p. P times negative 2 is negative 2p squared. And finally we get this quadratic for our final rate of change function. But we aren't done because what we really wanted was to evaluate this at a particular value. We were supposed to figure this when we had a unit price of $200. And again, recall that because the units on P are already hundreds of dollars, we really just want P equals 2. So R prime of 2 takes our revenue derivative function, plug in 2, and we get negative 4 out of there. The units on this are a little bit worse than what we might generally expect, but still manageable. So at a unit price of $200, this is our interpretation piece. Again, remember that being able to interpret the result of a derivative is one of the most important skills that we can build here. At a unit price of $200 per phone, revenue is decreasing. The decreasing is because of the negative. So just the fact that this is going downhill is what implies that we're decreasing. And then the actual rate, it just looks like 4, but when we pay closer attention to units, remember that demand was in thousands of phones, and that P was in hundreds of dollars per phone. So actually, the units on revenue are hundreds of thousands of dollars. So when we see negative 4, we're actually saying a decrease of $400,000. And then here's our units on P back again, our units on input. $100 increase in phone price. So although it's a little more complicated than our typical interpretation, that still fits the template. At a unit price of, there's our input, revenue is the function that we're studying, it's decreasing because its derivative is negative, and then the units on revenue are a little worse than normal, but it's still possible for us to trace this through. So units on output per unit on input. There's our derivative interpretation. So that's it for product rule. We'll be back in the next video for quotient rule.